Dear all, welcome to my presentation. First of all, let me thank you all for listening to me today. My name is Tuba Toprak-Cavdur. I am Assistant Professor at Textile Engineering Department of Uludağ University. Today, I would like to discuss sustainable nonwoven water technology for dyeing of cotton fabrics. The outline, my presentation is structured as 5 sections. In the introduction, I will provide you with some background on nanobubbles. In this section, I will focus on reactive dyes and cotton, and then we will consider about environmental impacts of textile. Finally, I would like to address the reason of the study. In the next section, experimental, I will show you materials and methods. The next thing I will share with you are results and conclusion. It will take about 10 minutes to cover these issues. After this, I can answer your questions. First of all, I would like to give you an overview of nanobubbles. Nanobubbles are 70 to 120 nanometers in size, 2,500 times smaller than a single grain of salt. They can be formed using any gas and injected into any liquid. Due to their size and structure, nanobubbles possess distinct properties that make them particularly effective at improving water quality, enhancing water treatment processes, and improving productivity in industrial and agricultural applications. Nanobubbles behave differently from larger bubbles because they are nanoscopic. All of their beneficial attributes are the results of their size. Nanobubbles are thermodynamically metastable for many months or even longer, in contrast to micron-sized bubbles, and have therefore enhanced gas transfer properties and greater industrial potential. These unique features enable nanobubbles to participate in physical, biological, and chemical reactions while also providing the most efficient gas transfer. The next issue is the reactive dyes. Reactive dye is a dye that can react with a fiber to form a covalent link, that is, forming a permanent attachment in the fiber and couldn't be removed by repeated treatment with boiling water under neutral conditions. Consequently, the dyes become part of the fiber, leading to outstanding color fastness to wash. Due to these advantages of full color brightness, range, high fastness, low cost, easy application, etc., reactive dye became the predominant dye for cotton dyeing and printing in textile industry since it was invented. Next, I'm going to focus on cotton. Cotton has many desirable fiber properties, making it a major fiber for textile application. It combines strength with good absorbency, for example, making it a comfortable and durable apparel fabric. Mankind first learned to utilize cotton more than 5,000 years BC in India and the Middle East. Finally, I would to raise briefly the issue of environmental impacts of textile. The production and consumption of textiles has significant impacts on the environment change. Environmental impacts in the production phase results from the cultivation and production of natural fibers such as cotton, linen, and from the production of synthetic fibers such as polyester. Manufacturing textiles requires large amounts of energy and water and uses a variety of chemicals across various production processes. Distribution and retail are responsible for transport emissions and packaging waste. During use and maintenance, electricity, water, and detergents are used. Chemicals and microfibers are also emitted into the wastewater. Meanwhile, textiles contribute to significant amounts of textile waste. Concretely, textiles consumption causes the third largest land use and water use in the value chain, the fifth largest material resource use, and the fifth largest source of greenhouse gas emissions. By the end of this introduction, you understood exactly why eco-design requirements for textiles and textile products are an essential tool to reduce environmental impacts of the textile sector and make the industry circular. For this reason, in this study, the usability of sustainable and near nanobubble water technology in reactive dyes was examined. In the study, woven cotton fabrics were used and supplied from Urac-Textile. The black, red, and blue reactive dyes were purchased from Archroma. Ingredients sold as dyeing extras were of analytic grade and provided by black. The dissolved oxygen level was controlled and the water taken from nanobubble generator was used in the dyeing processes. The reactive dyeing and washing cycle is given in Figure 1. The color coordinates were measured and color strength values were calculated using a conical Minolta spectrophotometer. Color strength values were calculated using Kubark-Munch equation. The washing fastness measurements of dyed fibers were carried out at test color fastness tester. Results. Colorimetry. Color coordinates of cotton fabrics are given in Table 1. A, B. Pilot of samples are presented in Figure 2. Nanobubbles resulted in lighter colors in all dyeing processes, in which they were used except in the one for the blue color. The effects of nanobubbles on the coordinates of colors on the red, green, and yellow-blue axis were different. For example, while nanobubbles reduced greenness and blueness in black, it decreased greenness and increased blueness in blue. Moreover, nanobubbles also caused increased yellowness of the red color. The results of Table 1, especially increased lightness values, could be explained by the possibility that reactive oxygen species, the proliferation of which was promoted by nanobubbles, could have degraded the dye. The degradation could also have been caused by nanobubbles increasing the oxidation reaction by increasing the dissolved oxygen level. This could explain the changes in AB coordinates of the colors. Figure 3 shows color strengths of the dyed fabrics. The presence of the nanobubbles in the dyeing bath caused lower color strengths, especially in black and red. Although the effect of nanobubbles on color strength of the blue color wasn't as significant as those of the others, it still caused a slight decrease. It has also been revealed in previous studies that the use of nanobubbles causes a decrease in color strength. This situation could have explained by the nanobubbles deterioration the structure of dye molecules by increasing the dissolved oxygen level, or the zeta potential of fiber surface cannot be reduced due to the adsorption of some of sodium ions in the dyeing medium onto the nanobubbles, and or the interfacial free energy and high surface area of the nanobubbles could have prevented the dye aggregates from accumulating on the fiber surface. Washing fastness. Washing fastness values of fabrics are given in Table 2. The washing fastness of dyed samples with or without nanobubbles were good to excellent level. The use of nanobubbles in dyeing didn't cause change staining of different fabrics except cotton. Nanobubbles, like other substances, could have effectively removed unfixed or hydrolyzed dye molecules from the fiber surface, resulting in half-point lower cotton staining values. In general, the reason for the high washing fastness values of fabrics after dyeing could be explained by the strong covalent bonding of dye anions to cotton. Conclusion. In the study, an environmental friendly textile process was designed using innovative nanobubble water technology. According to colorimetry results, the nanobubbles effective LAB values, obtaining lighter shades compared to traditional ones when using nanobubbles in dyeing could have been explained by the deterioration of reactive dye molecules. This situation was also supported by the lower color strengths obtained with using nanobubbles compared to conventional dyings. The effective removal of unfixed or hydrolyzed dye molecules from the fiber surface could have been effective in obtaining a half-point lower cotton staining values with nanobubbles compared to conventional ones. According to those results, it is concluded that it could be beneficial to investigate the use of nanobubble technology in detail, especially in washing. I would be happy to answer any question you may have now.